So see, it says we have to find the maximum wavelength of electromagnetic radiation, which can create a whole electron pair in germanium. And we know the band gap in germanium is 0.65 electron volt. So 0.65 electron volt is the energy gap that has been provided, and you have to calculate the wavelength. Just take a minute, use the relation that you have studied already in your modern physics regarding energy and wavelength, and try to find out the wavelength. So see, so electron gap, energy band gap that is given, Eg is given to us as 0.65 electron volts. So see, if we convert it into joules, this will be 0.65 multiplied by 1.6 into 10 to the power minus 19 joules. This will be the energy band gap in terms of joules. Now see, this is the minimum energy required to push an electron from valence to the conduction band, or to create a whole electron pair, which is mentioned in the question. So see, the required maximum wavelength, if I say the maximum wavelength is lambda, so energy and wavelength have a relation. Energy is inversely proportional to wavelength, and the constants used are h multiplied by c. So this is hc by lambda, and lambda here is the maximum. So this is the relation that you have already used in your previous chapters as well. So see, lambda maximum will be hc, that is 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by electron gap that is given, 0.65 into 1.6 into 10 to the power minus 19. So see, if you will solve this, this will come out to be approximately equal to 1.9 into 10 to the power minus 6 meters. So this is the maximum wavelength that will be created when electron hole pair has an energy band gap of 0.65 electron volts. So just note it down. We'll do 1 or 2 questions more. See, the second question says that pure silicon at 300 Kelvin has equal electron and hole concentrations of 1.5 into 10 to the power 16 per meter cube. Doping by indium increases the hole concentration to 4.5 into 10 to the power 22 per meter cube. Now we have to find out the new electron concentration in the doped silicon. So we have a relation, if you remember, just use that relation, then you will get the number of electron concentration. Yes, Fatima Faisal, did you try the question? What is the relation between number of concentration of electrons, holes, and the intrinsic concentration as well? We have done a single relation. 5 into 10 to the power 9. Yes, that's right. See, number of this question we have, this kind of question we have already discussed. NH into Ne is equal to Ni square. Yes, yes, you're right. Ne multiplied by NH gives square of the intrinsic concentration. So see, number of electrons that we have to calculate it. Okay, so we have to find out this. Number of holes, we already have number of holes. Number of holes are given as 4.5 into 10 to the power 22. Intrinsic concentration means concentration of electron and hole before doping. That was the intrinsic concentration only. So that is given as 1.5 into 10 to the power 16. So Ne will be equal to Ni square divided by NH. This is 1.5 into 10 to the power 16 whole square divided by 4.5 into 10 to the power 22. So this gives, as rightly said by Faisal, 5 into 10 to the power 9 per meter cube. Just note it down, then we'll do a small topic, filter circuits. Now see, we have already discussed rectifiers. We have seen two types of rectifiers. One was half wave rectifier, other one was full wave rectifier. For both the cycles, when we were getting input, that was full wave rectification, and the arrangement was the full wave rectifier. Now see, regarding filter circuits, see the output obtained from a junction diode rectifier. This is unidirectional by pulsating. So such a signal can be considered as the sum of DC signal superimposed with many AC signals. DC signals which are superimposed with many other AC signals. And harmonic frequencies can be different, and you have already studied harmonic frequencies in your 11th standard. So we can obtain DC voltage by filtering out these AC components. So two simplest filter these circuits, these devices which help in eliminating these AC components, or we can simply say by helping us obtain DC voltage. We can obtain DC voltage. So we can obtain DC voltage by filtering. So filtering what? Filtering out the AC components. Filtering out the AC components. So here we have majorly two kinds of filter circuits, and these devices are called filter circuits. Which these circuits which basically help in obtaining DC voltage by filtering out or eliminating the AC signal components. So one that we have are the series inductor filter, and the other one that we have are the shunt filters and the shunt capacitor filter. Majorly we have two types of filter circuits. Now see, regarding the first one, series inductor filter. In case of series inductor filter, we have a full wave rectifier. The way we have input with us. So how many diodes were connected in case of full wave rectification? One or two?
Two.
Two. So here also we have two diodes connected. Let's say D1 is connected over this side, and let's say D2 is another diode. This is connected over this side. So we have a full wave rectifier setup. Just the difference comes that we have an inductor along with it. And let's say the inductance is L. And this is connected in series with a load resistance, RL. This we have the center tap that I've told you in case of full wave rectification. And see, here you put the input, and here you get the output. So this is the arrangement for full wave rectifier with series inductor filter. Now see, this inductance L, this offers reactance that you had studied in your first term. XL, this is equal to 2 pi mu L. If you remember, XL is equal to omega L from your AC circuits. So this offers this much XL resistance to the flow of current through it. So clearly it blocks the frequency of AC component and allows low frequency DC component to pass through it. So a smooth DC voltage appears across the load resistance. Right, so this is how a series inductor filter works. Now see, in case of shunt capacitor, we have a full wave rectifier here as well. a full wave rectifier here is there. So again, we'll be having two diodes. Let's say D1 is the first diode, D2 is the second diode. Now see, we don't have inductor over here. This full wave rectifier is connected to a capacitor. So this is, instead of connecting to this inductor, now it is connected to a capacitor, which is in parallel with the load resistance. In case of the first one, means the series inductor filter, the inductor was in series with the load resistance. That's why we say the name series inductor filter. In case of shunt capacitor filter, what is meant by shunt? If you remember from your magnetics also, you must have done shunt has been applied to convert ammeter to voltmeter, or ammeter to galvanometer. These conversions, voltmeter to ammeter. So this is basically capacitor. Let's say a capacitance C is connected in parallel with the load resistance. So again, you will be having input and you will be getting output over this side is where. So now see what happens. This capacitor will also offer reactance. Xc. Do you remember Xc? You must have studied in AC. Capacitive reactance. What was the formula of capacitive reactance? XL is equal to omega L was for inductance, inductive reactance. Yes, Fatima. XC is equal to what? Yes, Faisal. Are you not even able to recall it through this formula? This was for the reactance one, for inductor. In case of, yes, anyone? Nobody remembers. It was omega C, 1 by omega C, which can be written as 2 pi mu C. Not omega by L, Fatima. Omega multiplied by L would give us the inductive reactance. 1 by omega C would give us the capacitive reactance. So now see what happens. The capacitor has this much reactance. So a high capacitance means more of C would offer low impedance, means less of Z, to a high frequency AC component. So what happened? It's so high that it's almost infinite. So impedance to low frequency DC component helps us see what happens. AC component is bypassed through the capacitor, or you can say it is filtered. So a smooth DC voltage appears at the load resistance. Just note down this point. This is just a very small topic, filter circuit.
Ma'am,
Yes,
both the filters, they allow only DC to pass through it, huh?
yes, both of them. It's just the difference comes with the placement of inductor in one and the placement of capacitor in one in the other. And the second difference that comes out in this case is the series and parallel connection. The rest of the things are same. Full wave based on full wave rectification. Mainly to obtain DC. We want to filter out all the AC components that are getting included in the total sum of DC, which is getting superimposed with AC signal. All right.
Yes, ma'am.
First, identify which one is forward bias, which one is reverse bias. Then calculate using Ohm's law whatever is the current flowing through this 1 ohm resistor. Yes, Faisal, right. It will be 2 ampere. Now see diode D1, this is P, this is N. So P is connected to the positive part. So D1 is forward bias or reverse bias?
Forward bias.
Forward bias. And see this is P and this is N. So N is connected to the positive. So D2 is reverse bias. So see D1 is forward bias. So it means this will offer zero resistance. This will offer zero resistance. And see regarding D2, D2 is reversed bias. So this will offer infinite resistance. So see, by Ohm's law, we can say simply if it will if D2 is reversed bias and it will offer so much resistance, means no current will be flowing. It will behave like an open circuit, so no current will be flowing in this arm. So ultimately, if we can reduce the circuit and we are left with this circuit only. This is the 2 ohm that was connected in the uppermost arm with the 6-volt battery along with the first 1 ohm resistor. So now see, by simply using Ohm's law, the total resistance, equivalent resistance will be what? Since these are connected in series, equivalent resistance will be 2 plus 1 is equal to 3, 3 ohms. The voltage is given as 6 volt. V is equal to IR. This is through Ohm's law. So we have to find out I. I will be V divided by R. So this gives 2 ampere. So just note it down. Okay, let's do one question based on rectifiers. Half wave rectifier and full wave rectifier. Just one question based on rectification. See, it says in half wave rectification, what is the output frequency if the input frequency is 50 hertz? So what is the output frequency of a full wave rectifier for the same input frequency? See the input frequency that is provided. Input frequency, this is given as 50 hertz. Now see, in half wave rectification, in case of half wave rectification, only one ripple is obtained per cycle of the output. Let me write this only. Only one ripple, or the curve that you say, curve of the graph. We have plotted the graph as well. So this is only obtained per cycle of the output. Now see, output frequency of a half wave rectifier, for calculation of the output frequency of a half wave rectifier, that will be equal to the input frequency only. So output frequency of a half wave rectifier, this is actually equal to the input frequency only. And the input frequency is what? It is 50 hertz. Now see, in full wave rectification, if you remember, two curves are obtained. Two curves, or you can say two ripples are obtained. So in full wave rectification, two ripples, or you can say those curves are obtained. Per cycle of the output, for every cycle. So see, output frequency for a full wave rectifier, as we have discussed this also. By this only you can figure it out. By the above statement, you can figure out that the output frequency of a full wave rectifier, this is ultimately 2 times the input frequency. That's why we are getting two curves. So this is twice the input frequency. So this will simply be 2 multiplied by 50, which gives us 100 hertz. Clear? Just note down this question as well. Written?
Yes, ma'am.
Yes, Fatima. Have you also written?
Yes, ma'am.
All right, fine. So this brings us to the end of this questions also of this chapter, semiconductors. See, now you will be having your revision classes and the schedule you can get it from Nishkarsh sir.